The figure below shows arrangements. The figure shows 4 arrangements of charged particles. Rank them according to the magnitude of the net electrostatic force on the particle with charge positive Q greatest first. P stands for proton, E stands for electron. Draw some force vectors. This is the force of P on Q, the P that's to the right. This is the force of P on Q. This arrow is a little bit shorter because this P right here is farther away than this P right here. In B, this force from the proton to the upper left has the same direction and magnitude as the one in part A, but now we have an electron which is exerting an attractive force, and this leftward arrow is as long or has the same magnitude as the rightward arrow in part A, except, again, it's in the opposite direction. In C, this electron to the upper right has this attractive force acting on big Q, and the proton to the right has the same repulsive force as does the one in part A. Let me line these up a little bit better. In part D, I'll do the force vectors. This electron, again, same as the electron in part D, a little bit shorter than the charge to the immediate right, or due to the direct right, because it's further away. And this electron over here has an attractive force, and this magnitude is the same as all of the other charges that are to the immediate right. So this is what I'm looking at as far as a final force diagram. Now I have to figure out which one of these nets the largest. I guess my first instinct is to do the vector operation tail to head. So I'm going to go tail to head with all of these vectors and then find out what the net vector is. So tail to head for that pair and then tail to head for this pair. Doesn't matter which one I go, doesn't matter which tail I use and which head I use, as long as I'm doing tail to head, tail to head. Same here, same here. And then I'll draw the resultant vector. So all I'm doing is I'm just leaning on basic graphical addition, vector graphical addition. So it's the first tail to last head, that's the rule. And then over here it's the first tail to last head. Oop, wrong arrow. First tail to last head. First tail to last head. First tail to last head. Okay, so you can see the resultant magnitude acting on that positive Q is greatest in scenario A and scenario D. Both of those have the same magnitude, different direction, but we don't care about direction. And B and C are tied as well. So this approach is leaning heavy on visualization. Make a bunch of drawings, think up as many visuals as you can, and put them to work for you. Okay, 3 bubbles, A, B, and C, start off with the same charge. A touches the grounding container and becomes neutralized, meaning whatever charge A had, it goes to 0. Then A touches B, B touches C, and then C touches the ground. And when C touches the ground, it must have had a charge of positive 3 because it drew a charge of negative 3 from the ground. That's what grounding containers do. They neutralize whatever charge touches them, whether the charge is positive or negative. So I guess I'm just going to do some storytelling. This approach I would call storytelling. Bubble C must have been charged. Let me write this down. Bubble C must have been plus 3 before contacting ground, before contacting the ground. And I'm saying that G and D means ground, because bubble C drew negative 3 charges from the ground. So again, that's reinforcing my claim that bubble C must have had a charge of positive 3 before touching the ground container. Prior to that, bubble B and bubble C contacted each other. It was that contact that made bubble C plus 3. So prior to that contact, bubble C must have had a charge of plus 4, and B must have had a charge of plus 2. Let me repeat that just for my own confidence. Bubble C must have gone into its contact with bubble B with a charge of positive 4, because after the contact, bubble C had to have ended up with a charge of plus 3, which means bubble B had to have a charge going into its contact with bubble C of positive 2. This is for sure the initial charge on bubble C plus 4, because prior to contact with bubble B, bubble C, prior to contact with bubble B, bubble C was in its initial state. Prior to contact with bubble C, bubble B contacted A. So bubble A and bubble C contacted each other. Prior to contacting bubble C, bubble A and bubble B contacted each other, which means bubble B must have had a charge of positive 4. And I'm saying that because when bubble B contacted bubble A, I know bubble A had a charge of 0, because bubble A had lost all of its charge prior to contacting bubble B when it contacted the grounding container. So now I can say I know for sure bubble B started off with a charge of positive 4, because prior to contact with bubble A, bubble B was also in its initial state. This means bubble A also must have had a charge of positive 4. All three of these particles started off with the same initial charge. So bubble A starts with a charge of plus 4. Let me sanity check this one more time, which means it really is helpful to write down your thoughts like I did, at least for me, because not only does it help you think your way through things, but it gives you something to double check. Bubble C must have had a charge of positive 3 before contacting the ground, and I know that because negative 3 charges flowed when bubble C made contact, which means, again, bubble C must have been positive 3. In order to attain a charge of positive 3, bubble C, prior to contact with bubble B, must have had a charge of positive 4. And bubble B must have had a charge of positive 2. Bubble B and bubble C touch each other. Bubble C goes from positive 4 to 3. I know that had to have happened. And bubble B, at this point, goes from positive 2 to positive 3. Okay, that sounds okay. Prior to contact with bubble C, though, bubble B must have had a charge of positive 4, and I know that's the case because upon contact with bubble A had a charge of 0 because bubble A was zeroed when it made contact with the ground container. Bubble A had 0 charge upon contact with bubble B. After the contact, that would explain why bubble A then attains a charge of plus 2, and bubble B, that's how bubble B went from plus 4 to plus 2. So again, I know bubble C must have started off with a charge of positive 4 because prior to contact with bubble B, bubble C was in its initial state. And actually at this point, I'm kind of done. As soon as I've proved bubble C has a charge of positive 4, I'm done because all three bubbles start off with the same charge. I don't think this was wasted effort though, because part B says how much charge goes through the wire when bubble A makes contact with the floor of the ground container. Bubble A had previously touched the roof of the ground container. Now it's going to fall to the floor. I'd already shown here, that's why it did help to write all this stuff down, that after contact with bubble B, bubble A went from 0 to 2 because that's how bubble B got its charge of positive 2. So the answer to part B is negative 2 charges flow through the wire to neutralize bubble A when bubble A hits the floor. Part C is asking how much charge flows through the wire when bubble B makes contact with the floor, and that answer is sitting right here. Positive 3 is the charge on bubble B, so negative 3 must be the charge flowing through the wire to neutralize bubble B's positive 3 charge. So part C was negative 3. Part B is negative 2. Part D says, during this whole process, what's the total charge transfer through the wire? And we know that answer really without doing a whole lot of thinking. That answer is, well, let's see, bubble A, B, and C all had a charge of plus 4 initially. They all have the same charge. That's the problem statement. And 3 charges times a charge of 4, 3 bubbles times 4 charges equals 12 charges. And these were positive charges. So if I have 3 bubbles representing or carrying a charge of positive 12, that ground container will feed negative 12. That ground container will draw negative 12 charges from the ground to neutralize those 3 bubbles, because that's, again, what grounding does. Okay, I have a positively charged ball. Let me indicate a bunch of little positive charges. This positive ball is brought close to an electrically neutral isolated conductor. Here is my electrically neutral isolated conductor. When this ball is brought near this electrically neutral isolated conductor, like I'm doing right now, the positive charges of this ball will repel the positive charges on this conductor. Conductor means these charges can move, so you'll get this separation effect. These positive charges will try to get as far away from these positive charges as much as possible. These positive charges will chase away these positive charges. In this situation, this isolated conductor is next connected to the ground, or grounded. So I'll show that like this. This symbol I'm drawing here, this little inverted tree, that's the symbol for ground. So all of these positive charges that are fleeing the positively charged ball that's being brought near it, all of these positive charges will escape through that ground connection, leaving this object with a net negative charge. Okay, the positive charges were chased away through the ground, leaving this object to have a net negative charge. If this red ball is then moved away, or basically just disappears, this gray ball will become neutralized. Positive charges will come back through that ground connection, and the result is a neutralization, or a net zero charged isolated conductor. So if that red ball is removed, the isolated conductor will return to its natural neutral state. If, on the other hand, this ground is removed from the gray ball with the red ball still nearby, I'm stranding those negative charges. So at this point, even if I do remove the red ball, there's no way to ground the gray ball, so the gray ball will attain a net negative charge as a result. Very similar to what you did in the Faraday ice bucket laboratory.